Symmetry. So it's time to put your thinking caps on. The first of our three educational speakers. Give it up for Kate Murch.
Thanks, Thomas. All right, choose your timer. All right, yeah, great. So, as Thomas said, I'm a professor here at WashU, and this is the educational science portion of the conference. So, yeah, you have to put your thinking caps on. We're going to get deep into quantum mechanics and sort of look at how the world all around us is not as it seems. There's sort of a what I call quantum indeterminacy. Not everything is known or knowable. It's very, as if a fellow up here has a t-shirt that says reality. What is reality? When you look at quantum mechanics, it really questions our notions of reality. So it's exciting. I'm an experimentalist. I have a lab a few buildings over, down in the basement. It's like a dungeon, although there's nice windows. And we cool things down to incredibly low temperatures, basically absolute zero. Study these microscopic circuits. We take data, we scratch our heads for 2 or 3 years, and we try to draw conclusions about big questions, like why does time flow forward, not backwards? Okay? And this is a question that I've been worrying about or pondering since I was a little kid. These days that go by so slowly, the days that go by so quickly. And now that I have the tools of science and the research we do, I'm starting to ask these questions in a more concerted way. So we'll see what quantum mechanics has to say about the arrow of time. And if you're not getting anything or not making any sense, you can shake your head, you can throw something at me. I'll slow down, I'll go back. I've got plenty of time here. So let's see what we have to say. So time seems to go forward. Do we all agree that time seems to go forward? Yeah? Well, why is that? For example, if I take this is not a glass, but I was hoping to have a glass here, but and I throw the can over there, and if you were to take a video of me throwing that can over there, it would be clear if you showed it to your friends that that video is playing forward, not backwards, right? The can doesn't just jump up off the floor, the dents don't become uncrunched, and it doesn't end up in my hand, right? So here I'm showing a broken glass. That's probably a better example. Why is that video so different going forward and backwards? Now, physics, we actually have a fancy name for this. It's called the second law of thermodynamics. It's actually kind of a rule of thumb. And what it means is that, well, it says entropy. You don't have to know what entropy it is, but it has to do with disorder and lack of information. This stuff, entropy, almost always increases. Okay? So it's not a very good law because it's not saying it always increases. It says sometimes it goes up. Mostly it goes up. Sometimes it goes down. So obviously we don't know very much about this. But a classic example is, say you take maybe my bedroom, it's very tidy, but later on it's more messy, okay? It's a tendency of things to become disordered, okay? Because there's maybe more ways that this bedroom could be messy than there are it could be neat. When it's neat, everything's put exactly where it should be, but there's an infinite number of ways for it to become messy. So it's much more likely for the room to be messy. So this is a tendency of cans to become bent and end up on the floor rather than in my hand full of soda. So that seems great, but if you look at the fundamental laws that govern mechanics, govern our physical world, Newton's law governed classical mechanics, how that can flies across the lecture hall, quantum mechanics even, how electrons orbit atoms. These laws, they don't distinguish past from future. Okay? The can looks the same, according to those laws, flying up toward my hand as it does flying away to my hand down to the ground. Electrons orbiting an atom, they look the same going forward in time and backwards in time. So if the laws of quantum mechanics and the laws of classical mechanics, the laws, our physical laws, don't distinguish past from future, why does time go forward and not backwards? Why does it go one direction at all? That's the question we want to answer. So just to sort of prove that point, that the laws of mechanics don't distinguish past from future, point at this idea of Poincaré recurrence. What that means is that if you start some physical system going in some way, if I throw that can over there, eventually it'll come back up to my hand and land in my hand. Okay? If we look at a simple system, we can see that in action. Okay? So this is going to be a video of a bunch of pendula. They're going to oscillate, and they're all different lengths. We'll see them from the side in a second. So what we do is, let's see if this actually plays. We're going to take these pendula, we're going to pull them up, okay? And then we're going to let them go and let them oscillate. They're different lengths, so they're going to oscillate at different frequencies. Look at that. So they're all oscillating together, okay? Then we watch, it becomes a beautiful snake, and after a little bit of time, this oscillation is just scrambled into chaos, okay? Clearly, we let the pendula go, now they're all disordered, right? That's the arrow of time. But something interesting happens if we continue to watch the video, okay? These pendula keep oscillating. They start to do a very interesting dance, coming back into phase. I think it's just beautiful how they interact with one another. They're not interacting, but how they make a collective motion just by rephasing. So if we wait long enough, everything come back to where it started. Just like that. Okay? So if I played this video backwards, it would look exactly the same as if I played it forwards. That's how the laws of mechanics don't distinguish past from future. What does that mean? That means that eventually that can over there is going to come back up to my hand. If I wait here long enough, the laws of mechanics say it's going to jump up in my hands. Now that is going to be challenging, okay? Because what we need is we need all the vibrations in the floor, all the motions of the air molecules in this room, all the vibrations in the can to be pointing in the right direction, to rephase, just like those pendula did, such as to jump it off the floor, back up to my hand, and land here, okay? So the laws of mechanics say that's going to happen. Now we might have to wait a long time. We might want to get lunch first. Because that time, the time for that sort of recurrence can be incredibly long. In this case, it's going to be longer than the age of the universe, so we definitely want to get lunch first. But isn't that fascinating that that would happen? Now, Einstein thought a lot about this as well. He made some phenomenal contributions to our understanding of space and time. And in particular, he says space and time, they're not that different. They're actually combined to be one entity. You just say it really fast. Space-time. Okay? So he says space-time, they're intertwined. They're one thing. You have to think about space and time together. Time is relative, space is relative, so forth and so on. Okay? So this is kind of a drawing of our world. We have these axes. That's what we talk about in physics. Plus x, that means like going to the right. Minus x means going to the left, forward and backwards. If I had a little more axes, room on this graph, I would do up and down. But you could think of these axes as describing this lecture floor here. So the laws of physics look the same if I walk to the right or if I walk to the left. I'm not sure if I'm walking to the right or left for you guys, but something like that. But this time axis, we have to include that too because we're talking about space, time. The time axis is very different than the space axis, right? It's these ones are symmetric. The laws of physics are the same going one way or the other, but time, we're kind of stuck going forward. Why is it that that one axis behaves so differently than the other ones if they're all sort of the same entity? Okay? Now, I'll give you an example. Say I show you a couple of photos here. Which one of these is in the past? Which one of these might be in the future? Even the way I ask the question implies there's a difference. Some of you may know, I don't think anyone's old enough to have been here, but this is actually the World's Fair, just over in Forest Park, around the turn of the century. That's clearly in the past. We can see these older boats, we see these old buildings, it's in black and white. See this picture here? This could be a picture of the future. I think it's actually from a video game, so maybe imagining the future. The future is full of possibilities. Okay? We don't know what is going to happen. And that's part of what makes the future so different than the past. We know what happened in the past. The future, who knows what happens? Okay. So hopefully I've suitably confused you, or suitably motivated that the fact that time goes forward and not backwards is it's something we should question. So that's my central question. Well, my central question is, can we answer this with quantum mechanics? Now, I already told you that the laws of quantum mechanics don't distinguish past from future, so this might be kind of pointless. But there are things in quantum mechanics that aren't described by the laws of quantum mechanics. And they have to do with information and measurement, and that's what we're going to talk about today. Okay? So, quantum mechanics. We have to learn a little quantum mechanics before we get started here. But I promise this is the most equations you'll have to learn. And I need one slide in this talk. Yeah, it's weird. But here's the plan. We really are going to learn some things today. I hope you do. The first is about uncertainty. And this is what we know about what we don't know, or what we can't know. Okay? And playing into that is this idea of wave-particle duality, that particles are waves and waves are particles. That leads into the idea of superposition. Okay, sort of this indeterminacy. Things can be at two places at once. And then we're going to get to the meat of the talk, which is really where we're going to look for the arrow of time, which has to do with this thing called wave function collapse, very technical sounding. How we acquire information about these indeterminate quantum systems. That's the plan. So, quantum uncertainty. Werner Heisenberg is known for this the Heisenberg uncertainty principle. And a lot of people have heard the phrase, you can't know the position and the momentum of a quantum particle at the same time. Okay? So what it says is uncertainty in the position times the uncertainty in the momentum has to be greater than some amount. Never mind that some amount is incredibly small. You can't know the position and the momentum exactly at the same time. Which is it might be bothersome. Because in our normal everyday world, I know exactly where this podium is and where it's going. It's sitting right here and it's exactly right here. Okay, but in reality, if I look very carefully, I can't know exactly where it is and where it's going. Okay, let's see. So delta x, that's where it is. Delta p, the momentum, the uncertainty in the momentum, that means where it's going. It's got a direction and a magnitude. Okay, so my phone always asks me, website wants to know my location, and it's like, okay, fine. So oftentimes I say no. But if it ever asks you if it wants to know your momentum, don't let it. That'd be bad. Okay? And it turns out that this uncertainty is just a mathematical effect of waves. Okay? It's something that I'll show you, I think, on the next slide. But the basis of quantum mechanics is really that we describe matter, particles, so forth, that can fly across the room. It should actually be described as a wave. Everything's a wave, but also everything's a particle. Okay? So waves and particles have to work together, I suppose. And so all these equations here, which you didn't actually have to learn, they're just a consequence of the idea that matter should be described as waves. Okay? So we just come up with the idea, and then we start writing down equations, and we have all of quantum mechanics. Pretty fun. So this wave nature explains some of the really interesting things in quantum mechanics. Okay, the first is the uncertainty principle that I mentioned. You can't know the position and the momentum of some particle at the same time. Well, let's say we have a rope going across this room, okay? And I shake the rope up and down, and a wave is started on the rope, and it goes across the room. It looks like this. Now, I could ask you, what is the wavelength of that wave? Now, it turns out the wavelength is related to the momentum. So what is the momentum of that wave? What is the wavelength? The same thing. Well, the wavelength, what does that mean? Well, that means we have to know what the distance between crest and this wave is, right? So we see a bunch of crests. 1, 2, 3, 4, 5, 6 crests, in about 43 feet or something. So I can divide 43 by 6. I turn out the length of the wave, the wavelength. Okay, so we can know the wavelength fairly well because we count several crests. But where is this wave located? Well, I don't know, somewhere between 10 and 40 feet. So I don't know where it is very well. If I can know the wavelength, I don't know the position. So waves are normally spread out over space. But if instead I take this rope and I just give it a quick shake, like say some little pulse in the rope, okay? So we can say where that is. It's at position 25 feet, right over there. Well, what's the wavelength? Well, can't say. I only see one lump. Can't measure the distance between crests. So the sort of interplay between knowing position and knowing momentum just comes from the fact that we have waves describing matter. Okay, the other thing that the wave nature gives us is this idea of superposition. You take two things, two waves of different wavelengths, say this one and this one. We combine these waves together, we get something completely else entirely. We get a superposition of those two waves. And if anyone's ever sang harmony, you know what I'm talking about. One person sings one note, another person sings another note, and the combination of those two notes gives you a completely new sound. Okay? The superposition of those two waves. Now this sounds really weird when we start to talk about particles or matter, physical objects. We're going to talk about physical objects being in two places at once, but that's really what happens. And I can show that to you by way of this sort of simple example. It's an analogy for our experiments. Okay, so what we have here is a box, kind of like this. And it's got in it two shelves. We've got a lower shelf and an upper shelf. Okay? And there's a ball in the box, and it can be on the lower shelf, it can be on the upper shelf. And I colored them blue and red just to help you keep them straight. So, a couple things about this box, and this is kind of what we do in experiments. If we send in a pulse of energy, maybe we shine this laser on it for a long enough period of time, it gives enough energy that the ball goes up to the top shelf of the box. Okay? Does that seem reasonable? Take some energy to get up there, maybe? Pulse it, it goes up to the top shelf. Another point is if I send a pulse of energy when it's on the top shelf, well, actually it goes back down to the bottom shelf. Okay, it's kind of like a dumbwaiter. You have to move the rope to get it to go up or get it to go down. So you put a pulse of energy, it goes up or down. Okay? What happens if I put half a pulse in? Half as much energy as I needed to move it to the top shelf. What do we think happens? Does nothing happen? Maybe half the time it goes to the top shelf? Maybe we don't care. Well, it turns out that half the time it goes up into the top shelf. Okay? So I put this pulse of energy and I check. Look in the box. It's in the top shelf, the bottom shelf, bottom shelf. Whenever I look, it's in the top shelf or the bottom shelf, but half of the time this half pulse works. It's 50% effective. That means that there's maybe a 50% probability of it being excited into the top shelf. Okay? But it's actually something much deeper than that. Because if all that was going on is a 50% probability of exciting it between one shelf and the other, if I apply two of these shelves, two pulses, nothing would happen. Let me show you. Okay? So I'm going to apply two half pulses. Now, some of you may be thinking, I know, half plus a half, that's equal to a whole. Maybe there's something funny going on here. Okay, let's see what happens. Well, if I apply the first half pulse, there's a 50% probability that we excite the ball to the top shelf. Right? That's what I said. Now, if I excite another half pulse, there's a 50% probability that the ball on the top shelf will go to the bottom shelf, and the ball on the bottom shelf will go to the top shelf. Okay? So we still have a 50% probability of it being in the top shelf or the bottom shelf. Right? So in that sense, the second pulse has no effect. But that's not what we find. What we actually find is we apply two half pulses, we move the ball to the top shelf 100% of the time. What does that mean? That means that there's some sort of stable state in the middle. Okay? If there wasn't a stable state in the middle, like this, then the second pulse wouldn't be able to move it back to the top shelf. Okay? So this stable state is something very interesting. It's this ball being at the top shelf and the bottom shelf at the same time. Okay? Crazy. Should I go back and do all that again, or does that seem... Okay, let me do it again. I think I have enough time. We know that there's this sort of crazy state where it's in both shelves at once. Because if it was simply the probability, like half the time it's in the top shelf, half the time it's the bottom shelf, that second pulse would have no effect. And we'd find we apply as many half pulses as well, and we always just get 50% chance of finding it at the top shelf or the bottom shelf. But when you do the experiment, we find, yeah, it looks like that. We find that we move it to the top shelf 100% of the time. Okay? And that proves to us as experimentalists that there's this superposition state, the stable state that's both the top and the bottom shelf at the same time. Crazy, but it's true. Turns out if I put in a half pulse of negative amplitude, maybe you can think about turning the laser upside down, maybe, what you would do. Then I create a different stable state. You see, this one here is blue, red. That one is red, blue. Okay? In fact, there's infinitely many possible states in this box. You have the top shelf, you have the bottom shelf. Those are the ones that we can see when we open the box. But we also have top shelf plus bottom shelf. We have top shelf minus bottom shelf. We have a little bit of top shelf. We have a lot of top shelf. All sorts of infinitely many combinations. And that's what we call a quantum superposition. And in quantum mechanics, we describe this by a wave function, which is just that, we just add these two things together with different coefficients. So these coefficients alpha and beta can be 1 and 0, or they can be a half and a half, or they can be 3/4 and 1/4, and so forth, and so on. So that's what we call a wave function. I don't know if you've heard that. Cool, but what happens when we open the box? We don't ever open boxes and we see balls on two shelves at once. That would wouldn't make sense in sort of with reality, right? So it turns out when you open the box, the ball's going to be in one shelf or the other. It has to be. Otherwise, there would be sort of an inconsistency. The ball can't be in two shelves at once. But it can as long as we don't measure it. That's part of quantum mechanics, where we think we're going to find this arrow of time. And Einstein was troubled by this to no end, because he knew these laws of classical mechanics, the laws of special relativity. He knew that when the can goes over there, if I can control exactly where it lands with how carefully I throw it. But quantum mechanics says, no, you can't know everything. If I put it in this superposition of two shelves at once, then no one knows. Not even God knows which shelf that ball is on. Okay? And he said that can't be the case. God doesn't play dice. But indeed, quantum mechanics does play dice. Okay? Yeah. So the process of looking in this box takes that superposition. The ball is in the top shelf and the bottom shelf at the same time. This really fantastical thing that really does happen. And it forces that ball to be in one shelf or the other. So we call it a collapse of the wave function. We had this combination of two things. We look in the box, now it's one shelf or the other. Looks a little like this. You can see this is the type of research we do here in St. Louis, because you can see the Gateway Arch over there. Well, it doesn't quite look like this. This is actually Periodigo. They blew up these old buildings several years ago. It's quite fun. Yeah. This is, some of you guys have heard about Schrodinger's cat. And let me tell you about the story briefly, just to show that this is exactly what I'm talking about. Okay, this is a sort of diabolical contraption where we put a cat in a box, okay? And then we hook it up to this sort of contraption over here, which consists of a radioactive atom that, if it decays, triggers a hammer that knocks open a vial of poison and kills the cat. Now, the idea is the atom is a quantum mechanical. So if we wait the right amount of time, there'll be a 50% probability that the atom has decayed. More so than that, it'll be in a superposition of decayed and not decayed. Okay? But that means that the hammer will be of both dropped and not dropped, and the cat will be both dead and alive at the same time, a quantum superposition of dead and alive. But when we open the box, the cat better be alive or dead. We're not going to look in there and say, it's dead and alive at the same time. We can't observe that because that would contradict reality in some sense. Okay? So the process of opening the box forces this cat to take a stand. Is it dead? Is it alive? And that's the wave function collapse. Now, the whole Schrodinger's cat story is actually, it has to do with sort of deeper questions. Does its consciousness have an impact on whether it's dead or alive? Can it know that it's dead and alive at the same time? So forth and so on. We can talk about this box for far too long. Probably long enough for that can to come back up in your hand. Okay. So my research focuses on measurement and understanding this process of determining whether the cat is alive or dead, or the ball is on the top shelf or the bottom shelf. And measurement's about acquiring information. What do we learn, and what can we do with that information we learned? Yeah, so how do we acquire information about what shelf it's on? We know that we can create this superposition of top shelf and bottom shelf, this really interesting state. And when we do that, we know nothing about where it's going to be when we open the box. It's truly intrinsic quantum randomness. Nobody can predict whether it's going to be the top shelf or the bottom shelf. It's actually, they use this technology in encryption and so forth. This is actually a very valuable technique. I imagine casinos would want to use this for their games because it's a really fair guessing game, because you can't know which shelf it's going to be on when we create this superposition. Okay, so let's think about how we can do a controlled experiment. We open the box slowly. So we're physicists, we like to use lasers, and we like to use detectors and make an apparatus. We have to spend all this grant money that we have somehow. Okay, so what we do is we put this ball in the box, and then we're going to shine a laser through the box, and we'll detect photons that come through the box on the other side. The idea is that if the ball is on the bottom shelf, it obscures the laser a little more than if it's on the top shelf. So we'll use this as a scientific way to measure what shelf the box is on, what shelf the ball is on. But first we have to calibrate our detector, okay? So what we do is we put the ball on the bottom shelf, we shine the laser, and we count photons. 3 photons, 2 photons, 1 photon, 1 photon, 5 photons, 4 photons, 0 photons. We don't get the same number every time because these are quantum photons. There's intrinsic noise. The same uncertainty principle I told you about before applies to the number of photons in a laser beam. Okay? So what we do is we histogram them. We think, just like you have a bunch of students in class, you make a bell curve and you say, well, here's the mean. You get A pluses over here. You get B minuses over here. At least that's what the WashU students get. So it's just like distribution, right? So sometimes we get more than 3 photons. Sometimes we get less than 3 photons. On average, we get 3 photons. Okay? So now we'll do the calibration experiment. We put the ball on the top shelf. We send in light. We count photons. And we get 5, 4, 3, 5, 4, 2, 1, 6, 8, 0, 6. On average, we get 5 photons. But again, we get sometimes more than that, sometimes less than that. So it's not a very good measurement because these two curves are overlapping. But that's what makes it interesting. In fact, it's a little bit like soccer. A lot of Americans complain that soccer is a boring game because there aren't enough points scored in soccer. But Europeans claim that that's why it's so interesting. Okay? In a soccer game, someone scores, maybe the scores are like 2 to 1 or 1 to 2, very low scores. It means that they're dominated by fluctuations. Did the person make it in the goal or did they not? And that turns out to make the game, that's what makes the game interesting. For example, you take 2 teams, we've got France and Italy. In a recent game, France scored 2 points, Italy scored 1 point. Does that mean that France is a better soccer team than Italy? Well, it's hard to say. It's just one game, and just a 1 point difference. So let's look at a few more games. Well, in these last 3 games, France scores 0 points on 2 occasions, 2 points on 1 occasion, and Italy scores 0, 1, and 2 points. So what do we conclude? Well, it's still hard to say. So let's look at even more games. Okay, this is now the last 100 years of games. Now we can make the same histograms we made with the photons. We get a picture of which team might be better. Now we have, on average, 1.5 goals per game for France, 2.2 goals per game for Italy. So maybe we can start to draw conclusions. But a single game doesn't tell us for certain which team is better. Okay? The same sort of thing is happening here. So we have to think about partial information. So let's say we put this ball in the superposition state. We send in the half pulse. Now it's the top shelf and the bottom shelf at the same time. We want to know what shelf it's on. Okay, we send in our laser and we get, say, some number of photons out, 5 photons out. Well, what does that mean? Okay, 5 is right here on this graph. We didn't know what state it's on, but now we learned some information. Now, say if I get 5 photons, is it more likely that it's in the top shelf, that is the red curve, or the bottom shelf, that is the blue curve? Does anyone have an intuition on that? The top shelf, right? Because if it was in the top shelf, it would be more likely to get that result. And that common sense is actually called, there's a formal name for it, it's called Bayes' theorem. It's Bayesian inference. So another equation, sorry about this, says the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. I always felt like that sounds like a peanut butter and jelly sandwich. So let's look at an example to understand how this works. We're in this lecture hall, right? And we don't know. It's possible that the sun could have undergone a supernova in the last 35 minutes of this talk. How do we know? We can't see the sun, right? The idea is that we would have maybe some sort of neutrino detector. The sun emits neutrinos when it's burning. And the neutrino detector can detect those neutrinos. The neutrinos come right through the roof of this building. They come right through the Earth when it's nighttime. Okay? So the neutrino detector knows if the sun is still burning. But this detector is kind of a tricky detector, because once it detects the neutrinos, it rolls 2 dice. And if the 2 dice come up 6s, then it lies to us. Otherwise, it tells the truth. Okay? So it's an unreliable detector. So we press the button and it says, yes, the sun has gone supernova in the last 35 minutes. Okay, so how do we understand what this piece of data tells us? Well, we can take our standard statistics, that is what we call frequentist statistics, and we can analyze this. Say, well, what's the probability that the detector is lying to us? What's the probability that I get double 6s? There's only one way to do that out of 36 possible combinations. So that's a 2.7% chance that the detector is lying to us. Okay? That's pretty good odds that the detector is not lying to us. 97% chance that it's not lying to us, so therefore we conclude, we bet good money on the fact that the sun has undergone a supernova in the last 35 minutes. But the Bayesian statistician says something different. He says, you know what? I'm willing to risk $50 saying that the sun has not undergone a supernova in the last 35 minutes. Okay? I think you probably guys would agree that we go outside, the sun will still be burning. So what kind of calculation did this Bayesian statistician do? Well, he said, this is exactly the same rule I showed you before, the peanut butter jelly sandwich. The probability of a supernova given the yes answer, okay, is the probability of a yes answer given the supernova. What's that? Well, that's the probability that the detector is not lying to us. That's 97%. Times the probability of a supernova. Does anyone know what the probability of a supernova happening in the last 30 minutes is? Low, yeah, right. So I thought it was about 0. And this is an easy math problem here. 0 times 97% is just equal to 0. So yeah, it's impossible that there's a supernova in the last 35 minutes because the probability of it happening is so absurdly low. So this same rule we can apply to understand which shelf this ball is on. Okay? It looks like this. The probability of it being on the bottom shelf, given n photons, is equal to the probability of it being on the bottom shelf originally. That was 50%. We know, because it's in the superposition. 50% top shelf, 50% in the bottom shelf. Times the probability of getting n photons given the bottom shelf. That's exactly this curve I showed you here. That's what we figured out. That's the distribution of photons we get when it's in the bottom shelf. So the intuition that if we get a detection over here means it's more likely to be in the top shelf is exactly backed up by Bayesian statistics. That's our common sense. Okay. So let me show you, we're getting there. We're understanding how we collect information about this quantum superposition. Soon we're going to watch these wave functions collapse. And then we're going to see, can we tell if that movie is playing forward or backwards? That's where we're going. Okay? So I'm going to simplify things a little bit. I'm going to just take these different shelves, and I'm going to make a circle, and the arrow is going to point to where the ball is. So if it's pointing over here, it's this top shelf plus bottom shelf. If it's pointing up, it's the top shelf. If it's pointing down, it's bottom shelf. We get anywhere in between, any combination we like. Okay, so it looks like that. And now we start detecting photons. So we get 6 photons. Well, 6 photons, that means it's more likely to be in the top shelf. So this arrow tips up a little bit, reflecting our knowledge of the system. We get 0 photons, that means it's more likely to be in the bottom shelf. So it tips back down. Okay, we keep collecting photons, and the state of this ball evolves as we collect information. And eventually, we find that, oh, they've got enough photons that we're pretty sure that it's in the top shelf. Okay? So that is the collapse of the wave function. So this time evolution is what we call a quantum trajectory, kind of a fancy term. But it's a picture of wave function collapse. It's a picture of the evolution of the superposition to something classical, definite. The ball is the top, the ball is on the bottom. Now I've been talking about this box with these shelves. In reality, what we have is a superconducting microscopic circuit made out of aluminum deposited on silicon. We put it in this microwave box. So there really is a box. Microwave frequency cavity. We cool it down to 1/100th of a degree above absolute zero in a dilution refrigerator, colder than anywhere in the universe, aside from other research labs here on Earth, maybe alien research labs perhaps. We cool it down, we use microwave frequency photons to do all this stuff, so it's very complicated, very fun. A lot of plumbing, a lot of electrical work, a lot of scratching our heads. And in the end, we get these noisy traces, These come from the photons we detect. So these are individual quantum trajectories. And you can see here's a green one. It starts off top shelf and bottom shelf. And it goes up and down. It's kind of noisy because we're detecting photons, and the outcomes of those detections are random. But eventually we find it's on the top shelf. Or sometimes we find it's on the bottom shelf. Half the time on the top shelf, half the time on the bottom shelf. But every collapse of the wave function looks different. Okay? So now the question is, which way does this movie play? Well, clearly starting here and ending here. So maybe this is how we can tell why time goes forward, because we acquire information in a certain way. We have to be more careful, though. Okay? The other question we ask, what if we try to play this movie backwards? Well, we can say, what if we find it eventually, at the end of the experiment, to be in the top shelf and the bottom shelf at the same time? Where was it before? That's the time reverse of what we had before. Okay? And that question, so if it ends here, where was it in the past? How does that information tell us about where it was in the past? Those movies look exactly the same as exactly the reverse as that. Okay? So these movies playing forward and backwards do not distinguish the arrow of time. Sorry. We have some really fancy movies my student Arian made for me at short notice, where we are actually tracking the evolution of this ball between these states. And we just decided to make it more interesting, so we're going to drive it between the bottom and top shelf. So it's going to go in a circle while we watch this wave function collapse. And we're going to look at the complicated quantum dynamics of this system. So let's see if this goes. So we're doing maybe 100,000 iterations of experiments. So each tiny little dot is one quantum trajectory, how this wave function, how this superposition evolves in time. And it spreads out because each iteration of the experiment leads to some different random quantum trajectory. Okay, so that's a movie kind of akin to that building collapsing, perhaps. Watching it over and over. Every time it collapses slightly differently. But what happens if we play this movie backwards? That is, if we end in this ground state, where was this quantum system in the past? Okay, it oscillates in the opposite direction. That makes some amount of sense. But the characteristic of this wave function collapse looks exactly the same, playing in reverse as it does forward. So far, when we look at this, the way these quantum superpositions behave, when we acquire information, we can't tell which way time is going. So sorry. So does wave function collapse explain the arrow of time? Not yet. So I led you on a goose chase, and now we just have to appreciate this building here. But it does give us some interesting tools. Okay, we all know that hindsight is 20/20. That's what we say, right? So say we think about a murder mystery novel. Now we know in a murder mystery novel, the murder occurs somewhere in the middle of the book, right? So there's some preamble, things happen, then there's some murder, and then the things that happen after. But to make the book interesting, there's some information blackout in the middle of the book, so you don't know who committed the murder until you get to the last page. So it keeps you reading, right? What if we had a murder mystery novel where the last page was torn out of the book? Okay? And we want to figure out what actually happened. Would we be better off reading just up to where the murder occurs, right, the midpoint of the book, or reading all the way to the end? Well, clearly you want to read to the end. You want to see what happened after the murder, before the murder, how people behaved. So in that sense, hindsight allows us to know better what happened in the past. This is what historians do. There's some event. They don't just study what happened leading up to the event. They look at what happened afterwards and before and use both of those pieces of information to determine what happened during the event. Okay? And so we can actually do this to understand how information really plays with the sort of quantum states and how they behave. So this is kind of a figure we made to sort of indicate how the past and the future both affect the behavior of a quantum system. What shelf the ball is on. Okay? And so it's actually kind of fair to say that in the quantum world, the future affects the past just as much as the past affects the future. Because it's all about information. Information later and before can be just as valuable. Pretty crazy. All right. So my central question was, does quantum mechanics explain the arrow of time? Not yet. But we're getting there. We talked about all these really cool things: quantum uncertainty, Heisenberg uncertainty, quantum superpositions. I hope you appreciate that the ball can be on two shelves at once. It's crazy. It's amazing. Measurement, wave function collapse. But the time symmetry comes from how we acquire information. And if that's symmetric in time, then that sort of maintains this symmetry. One more fun thing that we're working on in the future is we want to test causality. with quantum mechanics, okay? So say we have this state here. We want to stabilize the ball to be in two shelves at once. We want to make sure it stays there by making measurements and then applying controls to it. So we need a feedback loop. Feedback loops run our whole world. They will keep this room the right temperature, so forth and so on. We all come in here, the air conditioning turns on to keep it the same temperature. We want to do this in quantum mechanics. So the idea is we make a measurement. That measurement pushes the superposition a little bit. So then we have to process information, say where did it go, what do we need to do? And then we apply some control to move it back to where it was. Okay, that's a feedback loop. Let's try thinking about doing this backwards in time. Okay, what does that look like? Oh, well, first thing we do is we apply the control. So we do something to it, but then we have to make a measurement and process information to decide what control we would have applied. So it doesn't make any sense. The causal structure of decisions is turned on its head. But we can test whether or not this backwards in time propagating feedback loop works as well as the forward in time one. So some clever ideas how to do this. And it'll show something about causality. Does causality tell us about which way time goes? Or does causality work just as well in reverse? And just to prove that we actually thought about this, here's sort of a sketch of the experiment. We'd make lots of measurements. We'd make lots of rotations. We go back in a post-processing step. We process the data. We'll see what happens. So this is what we'll do in the future, just to show you how these ideas of time symmetry might impact our understanding of causality and ultimately perhaps free will. Okay, so if you're interested, we have a website that has links to some of our papers on the subject, both popular articles as well as scientific articles. You can check on the status of our dilution refrigerator, all sorts of fun things. This is my research group here at WashU. A lot of these ideas come out of discussions we have with my student Aryan over there. He's an expert in philosophy. So we discuss some of these things. We have a lot of support from Washington University. We have this Institute for Materials Science and Engineering. Also support from the Sloan Foundation and the John Templeton Foundation. So with that, thank you for your attention.
All right. That was awesome.